Okay. Welcome everyone to the SIG Apps meeting. I'm your host today, Janet, and I have our co-host Maciek here with us. And then we have one item on the agenda, which is a proposal for job queuing. Do we have someone here to talk about it?
Yeah. Can I present?
Sure. I think
Abdullah.
Yeah.
Yeah, I just made you co-host, so you should be able to share your screen.
All right. Can you see my screen?
Yes, we can.
Great. This is all right. Yeah, thank you for having me. So this is a proposal for Kubernetes native job queuing. What I'm trying to get from this presentation today is like mostly awareness. It's very early stages in the proposal. We have a detailed proposal in the document. Would love like any feedback that we can get on these APIs, our assumptions about how it could operate and the use cases that we're covering. The proposal has been public for a month now. We got a lot of feedback already, but I thought it's time to go around like relevant SIGs to present it. And then once the batch working group gets approved, hopefully we will be presenting it there, trying to push it forward within the working group, again, collaboration with the community. So the agenda, I'm going to describe the problem, the proposal, the APIs, and example use cases. So what is a job? Like what we're trying to do here is to focus on type of computations that run to completion. Basically, they have a start, they start, and they finish. They don't continue to run forever like services. We classified them at the higher level into two high-level categories. There are jobs that have multiple tasks run independently, like multi-color simulations. And there are types of jobs that run collaboratively. Like each job, there are a bunch of tasks that communicate with each other to process specific, to perform a specific functionality. Examples include like MPI, even reinforcement learning, and whatnot. One important characteristic of batch jobs is that they are often flexible on multiple dimensions. Sometimes they are flexible on time. They could run now, or if the resources are not available, they could wait and run a little bit in the future. They're flexible sometimes on location. They don't really need to run in a specific zone or region. Some cases they do because it depends on where the data is. But in many cases, they are flexible. Wherever the resources are available, they could run. They are also sometimes flexible on the type of resources. For example, they could run on any GPU model. Not like, for example, if A100 is available, they could run on it. If it is not, then they could run on, for example, K80 NVIDIA GPU. Another example is they could run on like standard or on-demand VMs, but if there is no, quota available, they could run on spot because they are cheaper. So what is the job queuing that we're looking at? What type of job queuing that we're looking at? And the high-level definition. It's basically like what we're trying to propose mechanisms to manage access to a limited pool of resources shared by multiple tenants. There are multiple tenants. They share a cluster with resources. Those resources could be auto-scaled or not. It doesn't matter. We want a mechanism by which those tenants are able to create these jobs. Those jobs will wait until they get a chance to run based on several criteria, whether the availability of resources, whether based on priority, whether based on type of resources that they actually want become available. And so we need that mechanism to allow the management of the jobs at the job level, not pod management, job management. And so why do you need job queuing? Again, like in many cases, tenants, they have lots of jobs, but limited amount of resources. And so you want a place where the tenant is able to create a job, just forget about it. It runs when it runs, when resources become available and whatnot. So on-prem, well, clusters are usually small and in scale and static. You can't auto-scale them. And so it's obvious that you would need queuing there. On the cloud, it's a little bit less obvious. On cloud, you still have limitations. For example, some customers want to utilize discounts. Basically, they purchase a committed use discount. They purchase from the cloud provider a specific amount of resources on a discount, and they don't want to use beyond those resources because they are on discount. For example, they buy 1,000 cores per month, and that's it. They don't want to use more than that, and they want to have their jobs only use that amount of resources. Also, some customers, they have spend limits to avoid cost overruns. They have specific like dollar budget. They don't want to go over. Also, you have per tenant limits, like some tenants, for example, they are higher per than others. And then there are also cluster size limits due to scalability. Like cloud sometimes is thought as like this utopia of infinite scalability, but that's actually in practice not true. There are always limits, whether it's at the Kubernetes level or whether it's a cloud provider. So at this point, I want to stop here before I go forward and see if there are any questions about this intro. Sounds good. So what users actually want from job queuing? Like obviously they want queuing. They want to be able to create jobs and those jobs to wait until capacity becomes available. They want the ability to express execution order. Higher priority jobs should run before lower priority jobs. Third, again, in a multi-tenant environment, they want fair sharing. Fair sharing is a concept that is quite common in job schedulers, where you want to be able to define like specific capacity per tenant and also be able to fairly share unused capacity. Third, they want to be able to specify budgeting, ability to say, okay, I want to use this amount of cores per week, for example. Ability to set policies where you're able to say who can use what and up to what limit. And last but not least, flexible placement across resource types, location, and time. And so why are we talking about a new controller? Why, for example, plain Kubernetes is not good enough? Well, the reason is that plain Kubernetes does not manage jobs at the job level. Any job that you create, whether it's a custom job or a V1 job, the control plane will continuously attempt to start the workload, basically create the pods, and the schedule continuously try to schedule the pods. There is no concept of fair sharing. If there are no available resources, it will work itself to death. Like continuously try to schedule these pods, they will not be able to schedule, and all the controllers continue to chug along doing nothing, basically. And the other thing is that Kate's quotas are not really enforced, are enforced at resource creation. They are not meant to do resource queuing. They are meant to basically provide a mechanism to protect the cluster from collapsing by setting limits on how many resources you can create in a cluster. So there are other open source, projects. The most prominent one is Volcano. The problem with Volcano that we see is that it reinvents scheduling. It reinvents job lifecycle management. They have their own definition of job API. It lacks proper integration with cluster autoscaler. Its production readiness is questionable at best. Like we're not really sure, like it's still in alpha since I don't know for how long. And it is led by a single company so far. Like it doesn't have this contributor diversity. It did not really get that traction to become like a core community project, let's say. Now, we had a project in GKE, and it's called Batch on GKE. Again, this is a decommissioned project. The APIs, I think, is still available in the Google Git repo. It has similar problems as Volcano. It reinvented scheduling. It is a schedule by itself. It has its own APIs. The other thing is it was initially closed source, and it was hard to meet customers' requirements of portability. So what are we proposing here? We're proposing a new controller called queue with the following design principles. First, don't reinvent the wheel. You want to no re-implementation of cluster autoscaler or pod to node scheduling or job lifecycle management. It should have native support for batch V1 job API, as well as the ability to hook in custom workloads like MPI jobs. The advantage of these, like applying these principles, is that we reuse significant existing functionality. For example, if there are new scheduling features, we don't really need to continue to, chase what the core Kubernetes community is doing. It has simpler customer adoption path. They could start by using, for example, v1.job, and then if they become big enough and require queuing, voila, that's it. Like they install queue, and then they are able to set up their cluster such that the jobs are being queued with quotas and whatnot. There are no concerns about functionality divergence, as I mentioned, related to new functions added to whether it's cluster or scalar or the scheduler, and also enforces separation of concerns. Again, it is not going to be a pod to node scheduler or a provisioner. It's just a job level manager. There are a number of concerns related to this model. The first is that it creates two layers of resource management. There's the job manager that does resource management at the job level, and then you have the scheduler, which manages resources at the pod level. We will discuss how we can resolve that. There are multiple components involved in starting a job, and so it adds extra latency, but we believe that is not, that is acceptable in the grand scheme of things, where you have a lot of jobs being running, and you have this like huge pipeline of jobs that continue to finish and new jobs starting. And before we get into the high-level design, we want to mention here that we tried to improve the V1 job API. We fixed and extended the existing API, fixed completion status tracking, which prevented customers from your users from using basically spot VMs with the job API. We introduced index job. We added suspended job, tracking ready pods and job status, and many other features. We're trying to continue to improve the V1 job API. We're also working on extending that in 124 and 125 with new features related to non-retrievable container exit codes, define a roadmap for scalable batch, V1 batch, to run millions of pods and thousands of millions of completions and thousands of basically pods running in parallel. So here's our resource model. And before we get to I want to describe what is our resource model. We're proposing to introduce 3 new resource types. The first one is called queued workload, which basically abstracts the representation of any job in queue. As I mentioned, we want to support V1 job. This is like the queue will support that natively, but we also want hooks to support MPI job or TF operator or Spark operator. Those jobs, they have their own controllers, they create the pods themselves, etc. They don't model their workloads as V1 job. We try to convince the community to do that, but there are always limitations to using V1 job. And so we still needed a way to abstract the queuing of a job inside queue. And so we're proposing a new resource called queued workload, where you represent the amount of resources needed for a job. We have a new concept also called resource claim. Again, all of these are proposals. Think of it as an API to ask for resources from cluster or scalar. Again, it's not necessarily the cluster or scalar we have in open source, anyone. Basically, we're going to say, we create a resource claim to, I want this amount of resources, and then the cluster or scalar would provision them and make them and mark the resource claim as satisfied, based on which we can reuse the resources. We have 2 main resources related to managing queues. The first one is, surprise, it's queue, which is a namespace resource. It's an organizing concept for grouping, managing, and reasoning about closely related tenant jobs. The other one is capacity, which defines, which governs a pool of resources and defines cluster-wide usage limits and boundaries of fair sharing. This is a cluster scope resource. So here, like I show the dependency model. Basically, a batch workload would basically create a queued workload that queue would be watching for and map to a capacity. The queued workload could be associated with the resource claim resource that gets created to provision resources before actually starting the job. We're thinking about two high-level personas for queue. The first one is the batch admin, is the one that sets up the tenants. Basically, a tenant here is a namespace. It creates the queues and the capacities and maps planned resource uses to capacities. And then the batch users. And the batch user, their user journey should be extremely simple, which is simply when they create the job, they set the queue name and that's it. Everything else should just work. So how this whole thing works. So I mentioned that we're looking at not recreating anything. We're just going to add a new controller called queue that does job management. And in this flow, I'm going to describe how this works. So at the top right corner, we have the user creating, for example, let's start with the V1 job. We're not looking at custom workloads for the moment. So they create a V1 job. They assign a queue name. For example, at the beginning, let's use an annotation. They can express that through an annotation. And then we would have a webhook that forces every job that's created to be created in a suspended state. So now this job exists on the API server. Queue watches for these jobs, notices a new job being created, and what it does based on the queue that is assigned to it, it will assign it to a capacity. So at this point, if we have an integration with a cluster or a scaler, before actually starting the job, it would, of course, check if there is capacity in the capacity, like this is the virtual capacity. And if it does, it will try to actually provision that capacity by creating a resource claim and waiting for cluster or a scaler to provision that to fulfill the resource claim in number 4. Once the resource claim is fulfilled, basically queue will unsuspend the job. Once the job is unsuspended, the job controller, the actual lifecycle manager of the job, will create the pods. The pods will be scheduled by the queue scheduler, and basically that's it. Once the job controller, once the job actually finishes, queue would be watching for finished jobs, and then it will reclaim the capacity. Are there any questions about this model, or is there anything that is not clear or ambiguous? Okay, let me zoom in a little bit on the cluster autoscaler integration. As I mentioned, we have this API called resource claim, where queue creates a resource claim object API that cluster autoscaler watches for, and it provisions resources based on the claim spec, and then marks it as fulfilled when the resources become available, after which queue will be able to unsuspend the job. This flow allows us, is a key enabler for location flexibility. Like queue or the scheduler does not know about future resources that will be scaled up by cluster or scaler. We don't know whether the capacity will be available in zone X or Y or Z, or whether the cluster or scaler will be able to provision, for example, model X or model Y of the GPU. And that's why this integration is critical to enable location flexibility in auto-scaled environments. It also handles stockouts. Again, the cloud, as you may know, we run into these stockout problems. And so the cluster or scaler will be able to say, okay, if it sees stockout and if the job is created to be in a single zone, it will basically scale up the zone where we have resources available. And it also will be able to handle both auto-scaled and non-auto-scaled environments. Cluster autoscaler has an integration, basically imports the scheduler code, and if there are existing capacity in the cluster, it will be able to fulfill the resource claim for existing capacity. So a resource claim does not mean that there will be a newly provisioned capacity. It basically means that the whole cluster as a whole has resources to fulfill this claim. And so we could, for example, deploy the cluster autoscaler in an on-prem cluster and do a similar job to what it's doing on the cloud, modulo the autoscaling part. Now the question is, how do we support custom workloads? As I mentioned, we have this concept of a queued workload. I don't know if I want to get into too much details here, but the idea is that for each workload that you're creating, we would need a controller or an integration from the custom workload controller itself to create a queued workload that represents the custom workload. This is what the queue will be watching for, and what it will basically what the queued workload will include is basically a reference to the actual workload, and the actual workload should support suspend resume of the workload itself. The idea here is that we would be introducing that as a sub resource, similar to like the scale sub resource, and so a queue would be able to start to suspend and unsuspend any workload without actually knowing the details of that CRD. So we are developing a proof of concept. It's a different piece, the queue control design. I'll leave it for another day. Probably Aldo will present that in the near future. How much time do I have, Magic?
We don't have any additional topics, so depends on how far you want to go. The overall call is until for additional 30 minutes. So if you want to leave some time for questions, I think that's reasonable.
Yeah, I'll try to finish in 10 minutes. So as I mentioned, we have first the job API. Everybody knows the job API that we have right now. Again, we're not adding anything to it other than the ability to specify the queue name. Hopefully, we will have this as part of the spec in the future. So the user journey, the batch user journey, again, it's going to be extremely simple. The only thing that you need to do is add the queue name where the job should be queued to get the resources. The queue API is also simple. It's basically sorry. So the queue API, again, it's a namespace resource. It only points to the capacity from which the resources needs to be allocated. The nice thing about this as a namespace resource is that like the namespace is the most natural way for users to discover what their queues, what queues they can submit, jobs to. And so creating a queue could be something that only the batch admin can do. And so they create the queue in the namespaces of the tenants, and then the tenants discover their queues basically by listing them in the listing whatever queues available in the namespace. We're also planning to add some limits here on a per queue level, but I'll leave that to the detailed document where we discuss more features related to the queue API itself. The queue capacity API is where the most interesting thing happened. It has, here I'm detailing the spec. The capacity API is a non-spec, is a cluster scoped resource that defines amount of resources that can be requested by the jobs starting through this capacity. Let me start with the requestable resources field. It's basically a list of resources that this capacity has. For example, here you can see CPU, and at the bottom you see NVIDIA GPU. For each resource type, you could have multiple flavors. We call them flavors for the lack of a better name. You could have, for example, here we call them like C2 standard. For example, it's like on-demand resources, and then you have spot. And the way that you would be able to specify that this is standard and this is spot is using labels and taints. Same way that we're labeling nodes, right? With just to differentiate between spot VM and standard VM. This does not map to actual nodes in the cluster. Again, this is virtual capacity that you have that can be concealed by jobs starting through the capacity. At the top, there are two fields here. We call the borrowing cohort and borrowing weight. Those represent knobs to control fair sharing. It's basically each capacity, think of it as a pool of resources. You could have multiple capacities within a cluster, each representing a pool of resources for example, a business unit. And then the borrowing cohort is basically an identifier that defines these group of capacities. They can share resources unused resources between each other. The weight basically determines for each capacity how much what is its priority in utilizing unused capacity. For example, if you have capacity A and B and C, and A and B, they are using their full capacity, C is using half of it, that half will basically be split between A and B based on the weight. This is a typical model, like you can see it in, for example, Slurm or Yarn, with slightly different ways of controlling it. Sometimes they use weights, sometimes they use explicit ceiling of how much you can use from others. And finally, like for each resource type, you are, as I mentioned before, you are distinguishing it from other types or other flavors using labels. Now, when queue starts a job by assigning it, for example, a specific amount of resources from a specific flavor, it needs to make sure that the job will actually use that flavor. And the way that we're doing it is by converting these labels into affinities that we inject on the job. And this is in the V1 job API. This is possible because of now we have mutable scheduling primitives on the pod template. For example, like if you see here, we have two types of CPUs. If Q decided that the job should use 10 standard cores, it will inject the labels on the core as affinity to force it to use that. I've got a bunch of use cases here that I'm going to represent through the actual design document. I'm just going to show one example and end the presentation here. So again, like here, you could have multiple namespaces. Each namespace represents a tenant. Tenant A could have two tenants, tenant A1 and tenant A2. You could have, you represent them using labels, for example, if there are those two tenants belong to the same high-level group. Again, the queues are namespace resources. You create these queues, they point to their own capacity. Notice that tenant A1 and tenant A2, they point to the same tenant A capacity. Tenant B, they have their own capacity. So that is like the simplest representation to address the use case where the admin wants to set quotas per tenant and how much resources they can use. And the resources could be CPU, memory, GPUs, whatever that the scheduler is aware of, any scalable resource, basically. An extension to this is, again, as I mentioned, if the admin sets the cohort as like the borrowing cohort, it basically means that tenant A and tenant B, they can borrow resources, unused resources from each other. If tenant A, for example, used all the resources available to it, it can burst into the unused resources of tenant B. And then we're planning other knobs, for example, to say, what if tenant B starts ramping up? What should we do? Should we preempt tenant A jobs that are borrowing resources, or should we just wait until they finish and then they get reclaimed, etc.? Those are all like part of the discussion that we're having on the document. So that's the, sorry, it was long, longer than I expected. There are a ton of details. Really, what I wanted to do here is bring more attention to this proposal. We are working on just going here as a summary. Again, where there is a proof of concept in progress that we're planning to open source soon. That we're hoping to iterate over with the community through the batch working group to refine the APIs, make sure that we cover all the use cases that the community has in mind. As I mentioned, the resource claim API is a proposal. We're trying, it will likely be also open source as well, or at least like every API is open source. We're trying to standardize a way to request resources from autoscalers. To make the experience for admins easy, we're planning a kubectl extension for creating queues and looking at queues and capacities and whatnot. And our North Star is to make it part of the K8s core APIs. And our approach here is to make sure that it works well with every existing functionality that core Kubernetes has. We don't want to re-implement anything. We want it to just work with the existing architecture and controllers. With that, yeah, thank you for listening. And I'm happy to answer any questions. And if there was anything unclear, please take a look at the document. There are a lot more details there that probably can give a better context than I gave you.
Does anyone have any questions? I'll let others speak before I'll ask my questions.
I had a question. The one thing that was unclear to me, so you want to do all of this work in tree, or were you looking at doing it as CRDs and then bringing it in?
Yeah, we're looking to build to prove of concept as a sub-project. Like I was discussing with Tim, we're saying like, look, proof of concept is worth 100 kips. Show that it works, show that it scales, show that the APIs are actually able to satisfy like communities' use cases reasonably well. And then we can start the process of, okay, trying to make it available in core Kubernetes. Again, that's what I mentioned. This is the North Star, but it's not what where we are starting.
Okay, then I guess here's the thing, right? So you call out Volcano and say that it's basically a single vendor solution that's being kind of really driven by one company, and it hasn't failed to get the kind of multi-company community support that the rest of the ecosystem has. Like, by introducing this, isn't it just creating additional fragmentation? Like, isn't it one more thing that's also supported primarily by Google that isn't, like, how do we avoid that? I guess is my question, right? Like, if your goal is to like unify the community around a standard framework for doing batch workloads on Kubernetes that adds value over what the V1 batch does today, that sounds like a great thing to me. But the plan for a community engagement is kind of, that's the hard part here, right? So like, how do you think we could do that? Right, that's a great question. So as you already noted, like we are starting from the core Kubernetes APIs. So that is something that the community already is grouped around, right? Like the scheduler, the job API, etc. So we want to meet the community where they are. We don't want to introduce new APIs for starting jobs and bring the community to it. So that is one thing. That's like basically the on-ramp part. Now, how do we bring the larger community and avoid that fragmentation? We are making everything available from the POC available, like and even the APIs from the very extreme beginning. The document has already went through some revisions based on the community's feedback. For example, moving the queue from cluster-wide API to namespace because we wanted to address specific use cases that we didn't have in mind.
We are starting the batch working group again in the same vein, and that's why we reached out to SIG Apps, for example, Magic and SIG Node to SIG Node and to other SIG scheduling folks like Wei, for example. He's with Apple right now. Like, it is a, like, how do I say it? It is like a main success criteria here is to make sure that we're presenting this and make some community, like have some community agreement around it before actually making it like to core Kubernetes and proposing it as a kit. Like, we don't want to say, okay, this is the thing, it is working, you have to adopt it the way it is, and then we are gonna force it into the core Kubernetes by creating KEPs and basically forcing what we've already developed and make it available in production into the community. Again, this is not something that is in production in Google or GKE. It is a very early POC, and we're hoping that the community would help us shape it, basically, the way that it works for their use cases as well. Now, the third thing that we hope it would not cause fragmentation is, again, we're not trying to re-implement anything. And that we feel is a barrier to adoption. We want things to work with the rest of the Kubernetes controllers, just like, seamlessly. And so we believe that this could be an enabler, basically, and yeah, that's, I guess, my thinking here.
So the other thing is, you said that Volcano was in alpha status, but I thought, my understanding is it's been in beta for a while now. And that, like, it's not really an early adopter thing, that it's used in production, like fairly broad. Well, I want to say that it's used in production at various largest companies across the industry. So, I mean, like, is there really that much of a concern about, like, in terms of building another thing for batch scheduling, is there that much of a concern around the stability, future, or scalability of Volcano?
Yeah, I mean, it doesn't have proper, it re-implements the scheduler. So it's basically a second schedule that you're deploying on the cluster. And so it's really not easy to use if you have a cluster that runs multiple types of workloads, for example. It doesn't integrate with cluster autoscaler. Like, it's not, the cluster autoscaler, for example, it imports the scheduler code. And so they need to be in sync to be able to make proper decisions. So that's maybe you can see this is a little bit tangential, but still, cluster autoscaler is under SIG autoscaling. It's part of the overall K8s, I don't know how I should, like, a community. So that is the other thing. My concern with Volcano is, again, I'm sure that if people put the time and effort, they will, make it like production really scalable. I have no doubt about that. I don't think that the model itself is not scalable. I don't think the model itself is non-production. But my concern is it re-implements things. It's gonna face, issues with like, it's harder to adopt from my perspective.
So I'm thinking that it's semi-related to what Ken was basically asking. Maybe we should, or we could, there are two parts of my question. One is how we can figure out and make the job extensions, because you did mention that ideally the queue would be part of the native batch v1 job. I wonder how we could make the default job resource updated in such a way that it could be reused by not only your queue solution, but maybe by Volcano and other solutions. So that's one thing. And I was talking earlier today with Ravi, and we were brainstorming on ideas. And he pointed that there's a project which is already a part of the Kubernetes SIG, which is Kubatch, which lays that kind of API on top of Kube. Maybe the question is, can we shape the Kubatch and towards the way that, I don't know, maybe your proposal is one of possible implementation, and we should focus on creating interfaces which we could embed in Kube, but the implementation details would then allow everyone to pick their or reuse their current solutions. If there are people who are using Volcano, they should be easy able to plug in into that solution. Similarly, folks with using I don't know, TensorFlow, if they could easily plug in into that solution. That's something that I was thinking
So
while listening.
yeah, Kubatch is Volcano in a sense. Volcano.
TensorFlow and Kubeflow and Volcano both leverage Kubatch.
Yeah.
And Kubatch, the one that in SIGs, I think is discontinued. Like, I don't think there are any commits to it. Has moved to be part of the Volcano package, and the development continued to be done there. It is the core scheduler for Volcano. Volcano includes, a job controller, right? So that's the project Volcano. There are multiple things in it. One is the Kube scheduler, the Kubatch, which is the scheduler, and then there is their own job API as well.
Yeah, Kubatch basically got subsumed into Volcano a while ago. I don't think
Yeah.
anyone's committed to Kubatch in like 2 years.
Yeah, but what I'm thinking is that instead of committing to a particular approach, if I'm basically building on Ken's question, what we can do towards making, because there is the concern of fragmentation already, and people already started building their own solutions that are very targeted at their specific use cases. So while working on it, I would like to see, I don't know, some kind of an effort where we could provide those interfaces where everyone could inject, rather than providing them with one particular. I left a comment in your document. Basically, when we were discussing several years ago the idea of adding workflow support after the initial part where we were done with jobs and scheduler jobs,
right,
we started building the next layer on top of jobs and scheduler jobs, which was basically some kind of a workflow, DAC support, whatever. And after the initial brainstorming and a couple of meetings, even we had a proposal that was actually merged into Kubernetes. We eventually decided to revert the proposal because the consensus was that we would provide people with one and only one correct way of running workflows, which we were aware that it wouldn't fit everyone. So I'm worried about something similar with this kind of approach. I'm not saying that it's a bad, I'm saying how we can maybe try to generalize this. If we want to include this in as a default component eventually, it would be nice if we could gather all interested parties' input and somehow provide generic solution, and then everyone could inject their own additional functionalities and build on top of that. Maybe that would be something much more valuable for everyone.
right. So that is why we're taking this approach like one step at a time. We're starting with a proof of concept with a sub-project. We're starting with the APIs being available to the public from the very early stages, explicitly mentioning all the set of use cases that we have in mind and targeting. My plan is to present this to the research user group in CNCF, which is, I think it's where Volcano is mostly discussed. We're presenting this there as well. We have KubeCon. I proposed a presentation about this in KubeCon. Hopefully it will get accepted. I'll try to get as much exposure as I can at the very early stages of this work to make sure it's either extensible enough or, okay, we get to the point, it is not extensible, it's not going to address specific use cases, and then it would be the decision, okay, this could continue as a sub-project. It's hard to make it as a core Kubernetes API, which I wouldn't be surprised if that was the case. But we need to start somewhere.
Yeah, I mean, it's not that we are gonna solve all the problems at a single shot. There's nothing stopping us to extend the current built-in types with those add-ons that allow those external projects to leverage the built-ins as much as possible. The question is, what are those missing bits that we just need to nail down? Yeah.
So, and this is what we tried to do at the beginning. If you notice, this is our engagement SIG apps a year ago. Okay, we figured index job is generic. It's going to solve a lot. It's going to open Kubernetes for more types of batch workloads. The idea of suspend, for example, just controlling jobs at the higher level, maybe trying to represent that as a sub-resource. Again, like we're trying to add these abstractions as we go. And it's a discovery process, to be honest. Like, I mean, the community has solved this for services and continue to do that. Like there is one set, like kind of set way of creating services in Kubernetes right now at the very low level, right? Like this is the service API, and they got to the next, like, you know, V2, I guess, after a while, after experiments with Knative, et cetera. We're trying to follow similar path of some sort. I do want to depend on core Kubernetes APIs. I want to build on that. I want to have the experience where if you are someone with a simple workload, you shouldn't need to like pick and choose. You start with core Kubernetes, you're going to have a nice experience. If your setup gets more complicated, you should just be able to add to it, not reinstall and bring in new thing and rewrite your YAMLs to use new APIs to represent your workloads. So that is my like hope, I guess.
I guess my question is, how realistic is that given the type of workloads that you want to support? Like MPI, that's an HPC workload. There's nothing simple about that. And even supporting that on top of commodity cloud can be extremely complicated given the way, I mean, usually like if you're doing this at scale, you're using InfiniBand, right? Like you're not even, Ethernet is something you can't use, right? So like, I'm not sure it's that. It's like if someone wants to run MPI on Kubernetes, okay, that makes sense, but it's not like they're not necessarily the typical user, right? Like it is a target community. It's an important community for Kubernetes, I would say, because I mean, like HPC workloads, they get a lot of core hours, right? But the same would be true of Spark, right? Like you're running a data intensive workload typically, and you've got a secondary scheduler that you want to implement on top of it, whether you're implementing like the Spark Mesos integration or the Spark Kubernetes integration. It's not like a super simple workload. So like reducing the barrier to entry for people who want to run more complicated workloads on top of Kubernetes, I think has always been a goal. And if you feel like this is the right abstraction for them to do that, but I don't think that the goal would be for a generalist software engineer who works in product development at a tech company to come in and just like turn up MPI.
Well, I mean, no, it's not. they will install MPI operating. That's what I'm saying. We need to support those custom workloads, but we need to have the right hooks to be able to provision the resources required for an MPI job.
Right.
So if you have that abstraction that you could say, okay, I'm an MPI job, I need these amount of resources and require standard VMs, not Spot, and they require GPU model, specific model, and VMs that are co-located on the same rack. You will be able to do this via queue, because we could extend the queued workload to have these provisioning requirements that can be relayed to the cluster autoscaler to provision that for you and then send the job there. And so these mechanics will be enabled by queue. And that's where like you simplify a lot, like a significant part of that journey. I don't know if that answers the question, but this is like HPC is becoming bigger and bigger on Kubernetes, also on the cloud. They have, as you mentioned, specific provisioning requirements that we need to relay to the autoscaler to be able to bring up those resources. So,
but I guess, I mean, the thing is, when I'm looking at the workloads that are already supported by Volcano, or at least if they claim are well supported, they are MPI, TensorFlow, Kubeflow, right? So, I mean, if your thesis is that the abstraction there is not good because it doesn't leverage native Kubernetes, or we could do better there, you know, I'm definitely, I support that conclusion in so much as, well, I don't reject that conclusion, right? Like, you know, I'm not a customer that uses that personally. So like, I don't know how bad that friction actually is. But if you think it's bad, I mean, like, you know, I definitely wouldn't push back on taking that to the working group and saying, okay, well, you know, maybe as Magic suggested, what we can do here is build a better set of abstractions, leveraging native Kubernetes constructs that we can all use throughout the community. And if you want to use Volcano, that's great. If you want to use our primitives, that's great too. Then we can, and that would be a good way to probably foster collaboration and adoption as opposed to creating fragmentation too.
Yeah, I completely agree. And again, like my biggest concern with Volcano is that it's an actual second scheduler. It competes with Kube scheduler. It does pod to node assignment. It is not. The
scheduler, you co-run the scheduler, the Volcano scheduler, at least you used to co-run the Volcano scheduler with the default Kube scheduler, right? Like we always had an architecture that allowed for the idea of multiple schedulers, and that was a design.
And there has always been problems with running multiple schedulers in a Kubernetes cluster.
I mean, they can fight, they can tight loop, they can wedge. It's not necessarily happy fun times unless you get it right. I get that totally, right?
And that's a big problem.
It is, but you have to look at it from the scheduler side perspective, like, because, you know, one of the things prior to Volcano and Kubi Batch that people were talking about was like, maybe we should, you know, modify the internal Kubernetes scheduler to make it more back friendly. But the reason they allowed for multiple schedulers, like Mesos had multiple schedulers because it was meant to be hierarchical. You had a resource orchestrator and then you had a specific scheduler per workload. Kubernetes definitely wanted to be more user friendly. So the default scheduler works very well for most workloads that people run. But for complicated batch workloads, it's not great. So the decision was made to like, we're not going to try to build that into the default scheduler. We would rather, for more complicated workloads, have a second scheduler that just does that well, right? So I mean, it wasn't like an accident; it was somewhat intentional. But if your thesis is that I think I can achieve very good results leveraging the default scheduler without heavy modifications, again, I don't think people would hate that experience. If it makes sense.
Exactly. Like what I'm seeing here is that what I think here is that we could have two level scheduler. Like there's a pod to node scheduler and there's a job scheduler. What we're trying to build here with Q is a job level scheduler. It basically decides for the whole job where it should land. And it uses the low level scheduler primitives to influence where that job is going to land using injecting other affinities and whatnot. So I think that this model is going to be more like friendlier and easier to use. More extensible because again, you build on existing features that Kubernetes has added to Kube scheduler. The problem with multiple schedulers, again, there are a number of issues there with race conditions, integration with autoscalers that is extremely hard to solve and hard to debug. And I feel this will actually reasonably solve a good chunk of use cases for batch workload, like this high level model, having a controller that manages the whole job and have APIs to request resources before starting these jobs, and then sending these jobs to those provisioned resources. But I get the point about fragmentation. I can't force Volcano to adopt anything we propose, but what I can do is I can try to make the argument that what we have here might, like, to find, how I say it, like, to find areas of collaboration, or like where we reduce that fragmentation. Again, I don't know how popular is Volcano. It's certainly like from my perspective, like from our perspective, is not popular in Google Cloud. I don't know about other clouds, but this is my only data point. Like, I can look at what our customers are doing. They're not using it. I don't know about others. Maybe there are. I'm pretty sure, like, other companies they do, but I don't know if it is available at scale.
But I mean, I know Huawei uses it. I can't speak to what everyone does internally. Again, I don't think there's going to be a lot of friction if you want to do this work and you think that it's going to be valuable to the community offering it. I mean, we're just trying to give advice, try to collaborate as much as possible with those projects in the ecosystem that already are live and already are kind of providing value. The other thing that's kind of like, when batch containerized workloads were first coming out, the idea was that, and this was like the Mesos kind of promise, right? Like, you're going to be able to co-locate your batch workloads and your serving workloads inside of your do-it-yourself data center, so you can get better SKU utilization by filling holes in your machine shapes with batch work when you're not utilizing it, right? So, like, one reason why I maybe Volcano and other batch workload schedulers that would be co-located in the same cluster with a serving workload scheduler aren't as today I don't think about the problem that way, right? Like, with commodity cloud, and especially with commodity cloud that offers me arbitrary machine shapes, I can totally co-locate all of my serving workloads in one cluster. And if I want batch workloads, I can just get another cluster with an auto scaler, stuff it full of batch work, and then let it scale back down when I don't need it anymore, scale to 0 if I'm not doing any, right? So, like, I don't get the same benefit in increased cluster utilization by co-locating batch. And this is anecdotal for me, for co-locating batch with serving workloads as I did 10 years ago. So, like, it could be the utilization thing could be like, we don't see it a lot because it's just not mature. It could just be that people are using different GCP services in order to orchestrate their batch work because they can get scale to 0 if they're mostly running Spark jobs. If I remember correctly, GCP has some managed services that allow you to stand up a standalone Spark cluster, scale it up, pull your data down from Google Cloud Storage, spin up your batch work on it, and turn the whole thing down when you're done churning your data.
I completely agree, but the thing is, like, I have two comments here. One, we're seeing more and more shift towards deploying batch workloads in Kubernetes. So that is actually a thing. I think people have realized that, okay, we've converged to Kubernetes as the orchestrator for containers. There are groups that are containerizing batch workloads, and their first answer to running them is, okay, how can we do this in Kubernetes? Because this is the standard now. And we're trying to find solutions for them. There are managed services, as you mentioned, for example, Databricks. They have their managed service available on all clouds. We have our own as well. But still, there are people who are, based on our user research, they have these large clusters. They want to deploy multiple types of workloads, and they only want to have one managed service, which is Kubernetes cluster, whether it's managed like GKE or on-prem.
I wasn't saying they wouldn't want to use. I wasn't saying they wouldn't want to use Kubernetes. Not to be confused. I was saying that the complexity of running multiple schedulers simultaneously for different workloads in the same cluster might not lead to the same benefit that it did like 10 years ago. And now, like, even if you want to use Kubernetes, if you wanted to use Kube and Volcano, spinning up a separate cluster just to run your batch workloads and scaling it up to meet the demands of whatever you're trying to run on it and letting it auto scale back down when you're not running any batch might be just as good a strategy as trying to co-locate your batch workloads in the same cluster as your serving workloads, or not. I mean,
Yeah, I mean, there are still use cases where you want to do that. Again, as I mentioned, you have committed use discounts where you always need to have your resources used all the time. Otherwise, you paid for something that is you're not using. The other thing is there are cases where you actually have you provision more than what you need just in anticipation of spikes, and we do see that, like there are cases for our customers doing that. There are provisioned capacities just sitting there because there's a flash sale or whatever is going to happen that will spike traffic instantly. And so they want that provisioned capacity available because provisioning resources is much more expensive than preempting a batch workload, for example. It's just like kicking out the pot. So there are still cases in the cloud that, have that model. But yeah, I don't want to keep picking on Volcano. I just don't think it is the right. I don't think it has the right APIs or support all the cases that we're looking at. For example, supporting flexibility. Cloud, as you mentioned, you have all these types of VM shapes and resource types that you don't usually see in on-prem. On-prem, you just buy this cluster, which is homogeneous most of the time. That's it. In cloud, you have so many types of resources with different costs and performance trade-offs. You want to provide a way for them to be able to fall back different, types of resources in an easy way. So that feature, for example, as well, is not implemented in. Volcano doesn't have the right APIs for it. So that's my pitch. Again, as I mentioned, we're trying to do proof of concept. We want to engage with the community from the very early stages. I'm planning to present this to the research user group in CNCF, which Volcano is part of. We will try to do our best. I want to say I'm just a representative here, but I honestly want to have leads from the community to shape this with us. Again, our goal is to have something portable. I don't want something that only works for Google. Just like we want Kubernetes to be portable.
Well, I can personally say that when you have a POC that you're ready to share it, I will kick the tires. I'd love to see it.
Yeah. Well, that's wonderful. And it's not complicated. We're only implementing the very basic use case for it, just to show how it's going to work. Again, we don't want to shape anything or make anything opinionated. I just want to have something, okay, look, this theory of operation that we're proposing, we implemented it. Let's see how we do other things. I'm happy if you're interested in and to contribute to it as well. All right, thank you.
Thanks. So I think we're at time. So I'm going to end this call, and then if you have questions, we can follow up offline. Maybe in the doc that you shared.
Sounds good.
Cool. Thanks, everyone. Bye.